Thank you for being here. I hope you enjoyed the lecture earlier this morning and the lunch. We're going to move into a Linux workshop. It's conceptual and the paradigms. It is being recorded, so you can refer back to this and we can share the slides with you in the end. Himakar Ganti, a doctoral student in aerospace engineering, will be presenting. And any questions about the materials or the cluster after, you can refer to me. Thank you.
Good afternoon, everyone. So I'm going to talk about you're just getting started in numerical computing or scientific computing. How to go about let us say you don't know anything about Linux, or so what is one of the best ways to get started, from nothing, you don't know anything about computers or anything, to all the way to where okay, if I have to use this is how my workflow or process should be. So how do we go about that? So that's what I'll be trying to show. I'm not going to do any programming. I'm not going to show any programming, but I'm going to show you the concepts that go into when you're writing a program. It's going to be kind of okay, when I'm writing a program, I have to keep these things in mind kind of thing. So let's start with some of this. So most of the exercises that we are going to do can be done in a Ubuntu terminal that you have, or a subsystem in Windows, or you can use a Mac terminal if you have one. So I might use my workstation in my lab to just show a few examples just in case. So that's one. And that's why we said you need to have access to that. And then what we are going to do is, what are the flavors of Linux we have, what are the computational paradigms we come across, and how to use Linux and through the shell terminal, and a few basic things about programming like shell scripting, writing your own programs. And then we're talking about how to do the same things on the ARC cluster, which we have been doing in the past couple of years or so. So we just talked about that. So why do you want to use Linux? So, well, where is Linux used? That's the first case. The reason they started using Linux is so that they can foster a culture of open source softwares. So kind of it was a community. Previously you used to have Unix systems where they were mostly proprietary, and you couldn't really modify it or you couldn't use it freely, or it was not available to the general public. But then they started using Linux, where they use the same shells and everything, or basically the same kernels. For most of the functions are pretty much common between Unix and Linux, and that's one of the reasons it's been so successful. And it's highly customizable, which means that you can tailor make everything from software libraries to settings to security settings to how you do your jobs to workflows, everything. And it can be clustered more efficiently. So when you go to the server space, you're mostly looking at Linux systems, just like George mentioned in the morning. You're not going to do Windows or Mac because it's got a lot of issues with clustering, and this has been traditionally what we have been working for a while now. So next is, what are the choices and flavors of Linux? And I'm going to go through that. So most of the servers in the US that we have seen is they use Red Hat, which is subscription based, where you pay to get the support, or you can use CentOS, which is mostly the free version of Red Hat but without support and stuff. And these are used mostly for high available systems where the availability is important, and you have to make sure that the system is up 24/7. So you can use it for background processes to run application logins, or head nodes, that type of stuff, or even compute nodes, and even in HPC. Debian base is mostly for desktop applications. So for Raspberry Pi, or where you're doing just development on your desktop, where you don't need supercomputing. And one of the reasons I wanted to mention that is it's user friendly. But then what's happening in recent years is, because of more number of users getting into it, they are adding too many features to it. So after a while it becomes just like Windows, too buggy and not too useful after a while. So that's why we generally try to stick to CentOS or Red Hat, where it is basically the Red Hat kernel that is being used. So it's less distracting and less buggy kind of. And then SUSE is just the European version of Red Hat. They pay for subscription over there, and OpenSUSE is free version of it. So you can pick whatever you want to. So these are some of the ones. There are more, but these are mostly the three directions that we have been looking at. So next we'll be looking at computing paradigms. So this is my favorite. So this was released, the Raspberry Pi is a $35 computer that was released in 2012. and it started the maker revolution. So I have a sample here if you guys want to take a look at it. So that's $35. It's a quad-core computer, and it has got 1 gig of RAM, and it also has wireless and network. It's got like so much features in it that you can connect sensors to programming. If you want to learn Linux or whatever, you can do it on that. And it has also been used as a data acquisition board in some labs where the sampling frequency isn't high. So it's like it started like, the DIY stuff, what you do, you can do in certain labs, they did it. So this started that. So that is a Raspberry Pi 3, the Raspberry Pi 4 that is been released this year. It's as powerful as a desktop from like 10 years back. So that's quite a bit. So it's pretty cheap, and it's been very popular with that. There are two ways to access this, using a remote shell or a desktop GUI. It's loaded right now, so if I can connect it to the monitor, it will just come to life. So that's one of the reasons why I want to show that. Next is consumer desktops and laptops. So I have my desktop laptop right here, right? So I can install Ubuntu in it, and I use it for mostly code development and stuff. But whatever I do, I can't run high performance computing codes or stuff like that. I can only use my computer to do explore certain features or add or remove. Just basically look at functionalities that I want to add to my HPC code, or debug some stuff or make sure some of it is running. So, and general purpose computing other than that. So most of them are 64-bit, and there are a lot of versions for it. So again, this also has two versions of logins: desktop GUI, which is mostly direct login, or we can use a remote shell. Then comes the supercomputing clusters, which is what George talked the whole morning today. So one of the most important things for this is, like he said, you need to have a specific facilities for it. Like cooling is a main issue, and you also have to have a dedicated team of administrators or people who are going to keep it maintained. These computers are mostly used for code development and production oriented tasks. These are not for where you can say you can just log into it and you can start typing on your code or debug your code on the fly. It's not for that. So you're running into a production run where you might have seen maybe a bug or something, you might want to fix it, but these are mostly for massively parallel jobs and production oriented tasks. So there's a reason we are trying to orient it that way. So you don't want to waste supercomputing time for others. That's one of the main reasons. So, and it's very efficiently managed with a scheduler manager. So there is one other paradigm that I haven't added here. That is the video editing, where people use consumer level graphics cards. So this year, the supercomputing cluster does have a GPU card in it, but that doesn't have any visualization ports. That's used purely for number crunching. It's not for displaying or visualization purposes. It's just for machine learning or data mining or any of the other stuff. So consumer level graphics cards are used mostly for video editing, live streaming, that sort of purposes, but that's not what we are going to cover in here. So these were some of the stuff. So GPU computing has gained traction recently, and one of the reasons is because of machine learning. So the difference between CPU and GPU in a crude term is CPU can do you have equations with several different options, right? One equation can have 8 or 9 or so. If the equations have in a same mesh, if certain grid points have different variations in them, the CPU can handle those intense tasks, but the GPU has to have more homogeneous tasks. So it can do homogeneous type equations or solve solutions more readily. So when you're doing data mining or machine learning, you're running the same sort of equations over your entire mesh point, or serializing codes or something like that. This is a better option to use. So that's one of. But then again, if you want to deploy your code on it, you have to adapt your code on it. You can't just pick and place your If you go to the cluster, you will have a partition that says GPU. You can't deploy it directly on that. You have to change your code to work it on the GPU. That's a different programming situation again. So once you have seen the hardware, what are some of the use cases we can run this through? So this was one of the cases that I ran. This is a direct numerical simulation. So I'm just going to give you an idea of a scale. That's just a 0.5 centimeter cubic domain. So it's really small, but it has got 18 million grid points. And the reason we had to go to that level is because we want to resolve turbulence completely. And then we are also looking at combustion within that. So that is a time step, and that is a grid point. So you can understand that it's computationally super intensive. it took me somewhere around 3 days on 512 cores for this to run. So we were able to capture some of the really, it looks cool, but it's much more intense, and that's just the velocity. So we have to capture temperature, chemical species, how the flame is going to change, all of that. That's much more intense than, there's a lot of post-processing involved. So we defined a metric for ourselves. So it is like cores into time. So I said, I used 512 cores, but then it's also running for 72 hours. So if someone is going to just use 4 cores and run it for 2 hours, so how do we measure that? So to get just a general idea, we mentioned a metric for CPU into cores, and we are using that to quantify. So,
sorry, can I ask you a quick question?
Yeah.
This is something that's come up to me before, because is cores, the number of cores, a linear measure of speed?
No.
Okay, because you have your measurement here of cores times time equals your...
It's not going to be linear because there's always going to be an overhead.
Okay.
Whether you are using a 8-core job or a 10-core job or a 100-core job, you will have a small overhead. In most cases, it scales linearly. These are large cases, so it's always going to scale linearly. But you're talking about really the low end of the core count here. So let us say you are doing 20 cores and you go down to 10. It may not show up that linearly.
Conceptually,
it should.
Linear is an okay measure to use.
Kind of.
I'm not talking about I need to make sure it's done within 72 hours. I don't want to be exact. I'm more of a service-based person.
Right.
I want to make sure
it's more of a general metric. You can use like a thumb rule or something. It's not
that's
like...
Perfect. That's perfect. Yeah, thank you.
So here is some of the work we did. So I just defined the metric, right? So that takes somewhere around 50-40 hours. That took me only 15 minutes on 8 cores, that cylinder case you're seeing. This is one of our more intense cases that my lab mate runs. That took somewhere around 240 or somewhere odd cores, and it takes 30 days to run to get higher order stats. And this is something, it took 24 cores or somewhere around 56 cores actually, and 1 month to run. That's a 3D case, you're just seeing it in 2D right now. So these are some really intense cases that we have had to run, and we have had success with those. So these are the type of studies we are looking about. And remember, I was talking about CPU versus GPU differentiation. Like the CPU can handle this, you see the droplets coming out, right? The GPU may not be able to handle that level of intensity because those are really intense. It's not solving one, it's solving multiple equations at every grid point. So it's pretty severe over there. So that was something I was interested. So most of the HPC stuff is used for solving problems like these. And none of these cases, I just wanted to add, is involving combustion yet. So if you add combustion in the mix, it becomes, it just goes up exponentially. It's a whole lot. It's a whole order of magnitude higher than what you need for this. So using Linux, I'm just going to go over some of the basics and what the shell terminal is, what some of the commands are. A very basic, just a primer. It's not going to be intense. So one of the reasons we want to use a shell terminal is it uses text-based commands, and it is universal. Like you can access a supercomputer through the shell terminal from Windows or Mac or even Linux type systems. And you can also, it's mostly text-based, so you'll mostly be typing in text commands. So you can use tab autocomplete for that. Now the next thing I want to show is why is the shell important. So this is what I came up with on my. Remember I asked you a question a while ago saying why it was what is the latency for not pushing a desktop window. He said desktop, the desktop that I'm seeing, the window I'm seeing in my laptop right now, it'll say consumes somewhere around 2 gigabytes of memory. Just as an example, you can't keep pushing that through the network line. It's gonna choke up the bandwidth. So what you want to do is you want to run faster, which means that you'll have to stick your black shell and just a text editor for that. So that's what I was trying to show here. So it's pretty resource intensive because you're trying to push this through the network pipeline kind of thing. So this is a Linux file system. So when you are looking at the hard drive, how it is organized or the data is organized. So you have the root folder at the top. These are all system commands that you can access. So if you want to show a listing of all your files, or want to find some examples, or ping, or just run a shell script or something. To run a shell script also you have to call a bash or something like that. So these are all the commands that are by default available to pretty much every user that's going to use it. This contains all the configuration files, and that's only system specific files. Standard users will not have access to any of these red files. When I say access, I mean modifiable access. They can't mod them. So most of the users, when they log in, they land here in their home directory. So these are all the standard libraries. Like let us say I want to run a formula application using C or Fortran. It uses some linear algebra libraries or some other specific combustion libraries, or some of them. They are stored in some of these folders, and you have to add them to your environment variable, which I'll show later. So what happens with that is when you're compiling and trying to run your executable, it knows where to look for those particular libraries because it has open functions in there. So that's one of the locations you can look it up for. And and again, the user is not able to modify any of these. They can have read-only access, which means that when they're trying to compile a program, it makes a copy for itself, of the prototype function or the header file for itself, and then creates an executable and takes it that way. You can't modify that. Next thing is, how are we going to log into our computer? I forgot to mention this, just like George said, you'll never be in the same room as a supercomputing cluster. So the only way you can access it is through remote login. And there are two ways to do it. One is SSH, where you directly log into the shell terminal. Other is using the SSH-X. The X is just let us say I want to use TechPlot for visualization or something, and TechPlot has been installed on the cluster. So what the X window forwarding does is when I type TechPlot in it, it opens up a graphical window, but it opens up on my screen, which is basically X window forwarding. So whatever the graphics window is supposed to show on the cluster, it shows up on my screen, kind of something like that. But it's not a full-fledged desktop like what it is. It's just forwarding only one window, so you're restricted to that. So yeah. So these are some of the commonly used shell commands that we are going to use to perform basic tasks, and most of them are located in bin or user bin. So you want to try that out, I can show that to you. So what is man command? I'm just going to do a basic listing of this. So let me show it to you. Do you want me to show it with an example? I can do that. It would be easier, I guess. So the reason we want to do this is this just lists the commands, and the way it works is I'm just going to log into one of my okay. So when I type ls, it just lists directories or any open files in it. So let us try with that. I just added an option to it. What does L mean? It's just showing is a long listing. When I say long listing, it is showing what are the options that it has, like read, write, and executable type of accesses, who is the primary owner, user, the group it belongs to, when it was created, etc. So, but one thing is, okay, let me do this. Okay, so it is listing the size of each of these files in byte sizes, but I want to do it in human format, so I'm going to do that. Oh, my bad. So now it is showing up in K and that type of stuff. So what it does is basically it is just showing in a readable format we can interpret for ourselves. One other option I'll show you is A. So basically what we are doing is we are trying to look at all files, and that's going to show if I have any hidden files in here. So that A shows all the files. So if I go to my home directory and run the same command, it's going to show all the hidden files. Any file that is preceded by a dot is a hidden file or a folder in Linux. So that's kind of one thing I wanted to show. It goes the same for pretty much all of the other commands. I mean, you can try them out if you want to, but it's up to you. So, yeah. Okay. And it's up to you if you want to try it. That's fine. If you want me to go ahead, I'll just go ahead. Oops. So you want me to? I can just go ahead, I think. Okay. All right. Okay, we have seen a shell terminal and we know what are some of the commands we are going to run in it, but let us say you're running a code or you want to change something. How do you do it? You have to use a text editor, basic. So the default text editor that comes with Linux is the VI editor, but it has got some restrictions in it. So it has been improved, and it is Vim editor is the enhanced version of it, where you can use a lot of add-ons, plugins, you name it. I mean, you can customize it to however you want. But no matter what editor you're using, you will have two distinct modes for every editor, a command mode and an edit mode. So here what I'm showing you is like some of the modes that we have used for it. So you can also set specific set it to use with specific settings. Like when I'm opening a file in the editor, I want it to show me the numbers, and if I'm using a particular language, I want it to show the syntax and color format, so I can use that. Now, one of the issues we have faced is with the encoding. If I have typed a file in Windows on Notepad or Notepad++ and tried to import it in Linux, I run into an encoding issue once in a while. What that means is like Windows encodes it differently than, even if I specifically set it to UTF-8, we have run into these problems where it doesn't actually encode the way Unix is or Linux is supposed to interpret it. So what that means is sometimes we have to write our code or type it out in graphics editor in Linux desktop and then move it or do it. But then if you're on the cluster and you just have to change only a couple of things, you're not going to use a GUI editor for it. You're just going to use a text editor, right? So how do you do that? So we're going to use a Y editor for that. So I'll go back to my shell terminal, and okay, so that is how it shows up. So you can see that it is showing up in colors, right, because I turned the colors on. So these are the settings that I'm using for the Vim editor in my workstation right now. So anytime I'm changing anything, there are three ways to do it. I did some changes and I don't like it. I can just type :q and exit. Or if I want to write the buffer to the file, I can do that, or you can write and exit. So there are several ways to do that. So this is just basically showing what those settings and what some of those settings can be for that. So you can use similar phrase. You can also search for specific phrases within that. Like sometimes we write code files that can stretch to 500 or so odd lines. You can't always keep parsing every line yourself manually. You can just look for a phrase and see if that's the particular line you're looking at. So and you can also do a lot of text editing. It's mostly keyboard based. You're not going to use mouse with it in all cases. Shell scripting and automation. This is an important thing for automating your workflow. So when I'm writing when I'm trying to deploy an application on the HPC cluster or even my desktop, what I have to do is there are multiple steps I have to follow. I have a compilation process, then I might like to have my data stored in very specifically in certain directories, or I want to make sure that only certain object files are changed. However I want to do it, my workflow has to be automated. What I mean by that is I can keep typing each of these commands in the shell terminal, or I can type them once in a shell script and keep running that over and over. So however you want to do it, it's up to you. But I rather prefer shell scripting because that's more homogeneous, because I don't have to keep changing the commands every time because it's hard to remember them. And the other problem will be is sooner or later if you're continuously developing or writing code, you'll be running into multiple code files. You'll not be using just one or two code files. You'll be using hundreds. At that point, shell script is also going to lag behind. You have to use makefiles with that, and that's the next step. But generally, when you're trying to automate your processes, even using it with some prepackaged libraries that can automate some of your workflow, you need to use a shell script to do that. And a shell script is also used for text parsing. So those are some of the applications that you use to do that, comparing files or extracting certain text. That is useful especially for your configuration files, like you saw the files in /etc or something. When you're doing changes, you want to look at only certain sections to see if those exist, or change kind of things. So this is an example of a shell script. All this shell script is going to do is it is going to look in those particular directories and give you a listing of the top 10 files that are largest in size. So here are a couple of notable things that go with it. This is called a shebang. So what it does is basically it is appending that to the title of the shell script. So instead of, normally what we do is bash is the command we use to call to run this executable. We don't have to do that anymore. Bash followed by the command script. You don't have to do that. You can just directly call the script file if you make this executable. So yeah, and it also uses regular programming languages or programming functions to do that. It uses for loops, if-else loops kind of thing. So you can do that. Then file permissions. Well, if you remember, I'll go back to this. Okay. So the permissions are these permissions. So read, write, and execute. So R is for read, W is for write, and X is for executable. It is for users and the group and the others. So the way our permissions are given is this first group of 3 characters is for the specific user. So if I created a file, I'll have read, write, and execute access to it. But I can restrict how others are doing it for. So I can make sure that others can only read it, some people can only execute it, so I can change how others are doing it. So the first 3 are for the user who created it or who owns that file. The second group of 3 letters is for the groups that it can be assigned to. Sometimes what happens is you can have multiple users or multiple administrators. So you want to give only certain accesses to certain administrators. You don't want certain administrators to like some of the updates or something. You just want them to look at IP tables or something. You just want to give them this access. So you will do that. You can just add them to the group and that group can have access to it. And then this is for everyone else, like people who do not belong to the group or to that particular username or something. So you can always restrict how each file is being used by everyone, and you can specify what it means. One more thing, D is indicative of a directory. So if you look at this is a directory indicated by that. L is just a symbolic link, or it just points to a particular directory that is there. So that's pretty much it for that. Environment variables and path. Okay, this is important. So what are environmental variables? Okay, when you are compiling programs or applications, you are going to refer to standard libraries, your own user created libraries, and some that are available in the system. So what you have to do is you have to know where those environmental variables are, which is basically your libraries that are specific, or I'm doing a vector matrix calculation, I need the linear algebra library, I need to know where that is located. So what this environmental path variable or path does if I know the value of it, I set this particular variable names to look into those particular folders, and it does that for me. So these have to be loaded at startup, or they can be sourced separately depending on your use case. So what happens is when you're compiling the program looks into those folders, sees that library exists from a whole bunch of libraries, and then it picks up the one, and it actually makes a copy for itself for that. So this is an example of a bash RC file in which all these environmental variables are stored. So you can see I have appended a path because I want to use OpenMP which is located in a particular folder for me, and I want to use the library from that. So this is pretty much all the paths that I've used in software applications for some of the stuff that I have done. You can also add aliases, which is basically a shortcut to exactly where the program is located. So every time I want to just access that program, I don't have to type the whole paths into it. So I can just get away with that, and you can customize it however you like for that. If you want to change your prompt color, you can also do that, and yeah. So yeah, terminal multiplexer. This is an important feature that I requested. So what this does is it's basically allows you to run your application after you log out. And the advantage of this is multiple. So when I started working in my lab on the workstation, anytime I log out, it kicks me out, in the sense it cancels all my running processes. So I can't really log out. And what happens is most of the time when you're working on superclusters, there is a job manager that takes care of it. So even if you log out, your job keeps on running. That doesn't always happen because on a desktop you don't have a job scheduler. So how do you do it? You can use a terminal multiplexer. All it does is basically you open up a window in that, let your code run or your application run, and you can just exit out of it and log out. It will keep it running in the background. So that's one of the ways we did it. So that's useful in certain cases. The cluster has it, but since we already have Slurm running for it, we don't need that. So for data transfer, we use secure copy, and the way it's basically is very simple, like, secure copy, target, and location. So it's like, if I'm copying this particular file to that particular location, I can just this is the source and that's going to be the destination kind of thing. If you want to use a directory, you have to use a recursor switch. So that's that. Questions so far? This is just a basic outline of how Linux works in the background kind of thing. Programming. This is not about how to do programming, but how a program works in the background, like when you want to execute and stuff. So I came up with something like this for it. So let us say I want to write a program on an application, right? What is exactly happening in the background? So this is a very crude idea or flowchart of how it works. So most of the time this is where we work. So this is our source code, like in our Fortran or C files that we are going to compile and run. It carries all our code. So if you look at I'll show you an example later, or rather I do it right now. So if you look at here, I have included a header file. What that is, it contains some standard libraries for print functions and other stuff kind of like. So what it's going to do is every time include more header files, it's going to include prototype functions from that particular header file. Now if you remember, we defined an environmental variable called c_path. What this is saying is this path points to the folders where those header files are located, just for the header files. So what the compiler does is, it takes those header files, look at which prototype functions it needs, and just makes a copy of the header file, or just creates the object files that are needed from the source files using those particular functions. So that's what you will have for object files, but it doesn't create the executable yet. You can do that in the next step. So generally when you're compiling or creating an executable, you have two steps. One is the compile step, and next is the executable or build path. So what it does is, if I'm using system libraries or some of the other libraries here, it will look into the LD library part, the several of the other environmental variables where those libraries are located or those objects are located, and then it will make a copy of them for itself, and then it will create the final executable for us. So basically the way it works is, it will look for header files, create object files, see if it needs system libraries or other libraries, and then finally create the executable. The executable can have an input and an output, but it depends on how you are going to do that. So this particular print function is located in that header file, which is fetched using that variable. That's kind of the thing. So if you remember, I just talked about shell scripting a while ago. I can do all of this in just one step in the shell path, because I can name whatever I want for this, for my source files, and I can have more than one. So I can just ask it to compile and execute in the same step. I don't have to keep on changing or typing on the terminal myself. So that is useful if you have got a few source files, like let's say you have 5 or 10, that's okay. We can keep typing or adding them to the shell script. What happens if you have hundreds? We use makefiles. So makefiles is entirely a different story again. What it does is, it takes the source code files, compiles them, and builds an executable from that, depending on, we can set separate library paths for it, and we can also set separate flags for it, how we want to do it. So this is a makefile I used for hybrid programming. So I use C and Fortran in two different source code files, and create an executable from all of that. So what you're seeing here is you have different compilers here. So it's basically going from the compiler is giving you the object file for C, for Fortran, and then you're making it up with all the system libraries added. So even though your source code file is say 10 kilobytes or something, your final executable can be 1 MB or so, because it is copying the libraries from the system. It copies those object files, so that when you run the executable, it's totally standalone. It doesn't have any dependencies on other libraries for that. Well, questions on this is yeah, that's fine. Okay, parallel computing and HPC. Well, this is what George was talking the whole morning. of this session. Well, all HPC is, in a very layman's term, is a bunch of computer nodes and cores that are combined together with a high-speed network to make sure that they have sharing of memory and cores that they can be used. But one of the crucial things is for any code to run on a HPC cluster, you have to parallelize it or use some of the parallelization libraries to make it run, which is OpenMPI and OpenMP. So OpenMPI uses cores. So if I have a very large grid, I want to spread it over like 100 cores, I'll use it using OpenMPI because I can do it directly. OpenMP is threads, and the way it works is a bit different, but the overall concept is pretty much the same. So, yeah.
Can you explain really simple terms? Let's say I have a fairly simple project,
Mm-hmm.
but it's large data.
Mm-hmm.
And the difference between, I'm trying to think of a way to put this because
Sure.
This is not my background. I have a regular desktop. It's okay, it's pretty good.
That's fine. Good.
But the difference between this and let's say HPC or parallel computing, just kind of in reference to how it works versus a regular just simple desktop, which maybe has a few cores or something like that.
Right. The way OpenMP works is, let us say I assign 1,000 cores to a job, right? Just as an example. One of the cores acts as the manager or the master. So it is going to pass on instructions to each of the cores. It is going to divide the array into chunks, where it passes each of those chunks to each of the individual processors' memories, and they do the calculations and the data back. So OpenMPI does that. So what it is doing is it's dividing the task into as many cores as you have available, -1, which is a master, and then it spreads it out.
And that's the same as parallel computing? Is it something different?
It has got a lot of other ways. Parallel computing it's partly that, but not entirely. What parallel computing can be is I can have 10 different workstations. I can combine them with a high-speed network and say I'm doing parallel computing. That's one way to look at it, but it depends on how you're going to do it. HPC is basically parallelizing your job over multiple nodes that are connected by high-speed fabric network. That network is the backbone of the computing infrastructure. It's the cores, yes, but it's basically that, because every message that you're doing for OpenMPI or passing messages between CPUs to say where your memory address is for a particular data type or something like that, that happens through that network. So that network is like the backbone of how it's all put together.
It's really important, I think, for explaining some of these tools to other individuals is in context of I do a lot of raster imagery. And so I'm thinking as the more cores, the more chunks of my grid I can send to.
Right.
So instead of running 1 million calculations on one core, I can divide it by 10.
Right.
Each
right.
one
Right.
a tenth of that. Is that kind of actually make sense?
Yeah.
Okay. All right. I just want to make sure I'm on the same page.
Right.
Because again, could use some of these tools, and I have another question for both of you later on. But most of my job is going to be helping explain these tools to others, working with Amy. So I just want to make sure that I conceptually understand, so I can tell them the right directions or something. So sorry, I keep interrupting you, but
that's fine. That's fine.
Explain.
So OpenMPI, what it does is, let us say I have only 10 cores on my workstation or something, and I split it into 16 cores. It will run 10 cores first, and it will wait for those 10 cores to finish before it pushes the next 6. It's the same with OpenMP, but OpenMP can spawn more threads. So even if I have 10 cores, I can have 20 threads running. But if the thread is really fast enough, it's just going to execute faster. But again, it's depending on how you want to choose it. So you can have more threads than cores, but with OpenMPI, you restrict yourself to use only the number of cores you need, so that you're not overstressing the system or oversubscribing kind of thing. It slows it down, basically. So this is what it's a very crude. This is not a good image as George was presenting, but this is what it is basically. So this network is what everything is connected to. You share the cores, the memory, and the cache kind of thing. So basically what happens is when you're splitting your data into thousands of chunks or thousands of cores, you have to have each of the cores, you have your grid, right? So let us say I break in the middle, but when one core is done, that data has to be passed on to the next core. So you have ghost nodes for that. or ghost points for that. That memory has to be shared between corresponding cores with the tag numbers or identification numbers where they do it. So let us say I have core 1 that has to send ghost data to core 2 because it has to follow up on the calculation. It will do that and it has to know the memory register for that, where that location is for that data. So that's why this is important. So that brings us to the ARCC, what it is. Any further questions before? Okay. Well, right now we have got 36 nodes with the Intel Xeon processors. It's a 2.4 gigahertz, 20 core or 40 thread type processors. And each node has 2 processors and somewhere around 192 GB of RAM. That's what my advisor told me. It also has got the GPU cards in it. Like if you remember, I showed you a GPU card, right? So it doesn't have any visualization outputs. So those are used for data mining or homogeneous type computations. They have one of those examples or cards can have 3600 CUDA cores or compute cores. Those are smaller compute cores that can do numerical calculations much faster when you're doing data mining or looking for minute patterns and stuff. But they are more for homogeneous type calculations where you're doing the same calculation for all the mesh points or grid points. It's not for CPU intensive tasks where you're looking into solving multiple equations or differential equations for that. So that's what, and it uses a Slurm scheduling manager, and it also uses directory services which means that using your 6+2 you can directly log into ARCC provided you have access for that. So in the next step I'm going to show you how a Slurm scheduler works. So it's basically trying to control how information is passed back and forth. It maintains a database and it's going to run its daemons on each of the individual nodes, and when you perform a Slurm command, you have to make sure that it has to make sure that the resources are available for that particular job to run. So these are some of the common commands that you use for Slurm. So using the SQ command, this is what I had, so I can show you what's running on the cluster right now. Let me demo that. So that's jobs running on the ARCC right now. So he's running a Jet-in crossflow case. Jeremy is running a Jet-in cross. So you remember the large AD simulation I showed, right, that I said was running 30 days. This particular run is one of those. So we had to have 10 of those runs to do our machine learning algorithm on. So he's using 17 nodes for that. So this shows how many nodes he's using and what those nodes are, because each one has a host name. So he's been running it for a while now. Yeah. So using the sbatch commands and slurm commands, you basically try to manage your job on how you're running it for the cluster. I'll come back to that again. So how does the slurm script part look like? So these are the sections of a slurm script. You remember I talked about shell scripting, right? So to the shell script, if you add some of these commands, if you use double hashes, it becomes a comment. Sbatch or slurm neglects that. But in general, if you just use one, it's just going to take it as an sbatch command. So capital N is the number of nodes I want to use, and tasks per node is, when I was doing the DNS, I have to always use in powers of 2. So I could use 512 or 1024 or 256. So the maximum I can use in power of 2 for one node was 32, and I use 16 nodes with a total of 512 cores. Now this is the time for which you want it to run. The hard limit right now set in the cluster for runtime is 20 days, no matter how many cores or whatever you are using. So I wanted to run it for 10 days, followed by hours, minutes, and seconds. This is the file where it captures all the screen output. So when you're running simulations, they do a lot of screen output in terms of time steps, like what your temperatures are or average quantities are, kind of like that, and residuals are. So that can be captured in that, including compile errors. This is just the name of the job. One of the advantages of Slurm is, because it has been integrated with directory services, is I can send notifications to myself with start, when my job starts, when my job ends, or it fails. And these are just your regular, like, MPI or shell commands that you're going to. Basically, in this file, it has basically taken care of all the steps for MPI for me. I know in this file it has, I encoded, it's hard coded, like, the number of cores I'm using right there is hard coded one of these files that's specific to my particular application that I was running in. So that's how here is where you'll be like using your MPI run cases, like when you do MPI run. So that's where you'll use it. Now, I like to add 3 seconds to each of these commands, because when it is compiling, there's a chance that it might, everything finishes in finite time, so it's better to give it a couple of seconds to relax before I start sending in the next command. So that's why I use that. And this is for data management. So if you want to create any directory specifically or something, you can just do that particular folder. This is important, do's and don'ts for the ERCC cluster. This is something that we have run into in a few times in the past. What should we use the HPC cluster for? Well, CPU heavy tasks or GPU heavy tasks, like DNS, direct numerical simulations, where you're solving for everything. Large AD simulations where you want to run it for millions of grid points and a lot amount of time. Combustion sensitivity analysis, those type of runs. Even like heavy mathematical fine-tuning of parameters or stuff like that. We should always use a Slurm script, because one of the reasons we should is the execution of any commands on the head node has been disabled. That is because the head node is responsible for all remote logins, everything, like all the incoming and outgoing listings. So if I just say like MPI run or something without a Slurm command, it's going to run on the head node. So for that reason, execution on the head node has been disabled, and it's always beneficial to run, even if you're doing a single core run, to run with a Slurm script command. Well, if you're using GPU computing, you have to translate your code to to work with that particular hardware. You can't just use MPI code and say, okay, just use the GPU partition. You have to recode it again in CUDA or whatever language or toolkit you are going to use. Otherwise, it's not going to run prior to execution. And it's always useful to use any notifications, because that way you know how to schedule your next job. So that's that. Well, we have had cases where people were running single core jobs on the cluster, and we don't want those, because if you can run if it's serial code that you're just running with just say one particular set of equation that you're just iterating over and over again, it's better to run on a desktop or a workstation which has fewer cores or higher base clock speed for the CPU. You don't want something of you don't want thousands of cores for it, right? It's just you have to finish the first iteration before you go to the next. It's serial. So there's no advantage when you try to use it for those particular cases. What other thing we should not do on the cluster is we should not use it for visualization, because it's just going to slow down all the resources for others, and it's not enabled. Like, you want to do batch conversions of files from one format to other, use Slurm script, and if the application installed, you can do it. But our suggestion or recommendation or our practice is, it's better to do it on a workstation in your lab or at your workplace. And the last one is important, because we have had people do that too. Use cluster partitions that only you have access to. Like low-end GPU are the defaults. So, like for example, is if my advisor gets in a few nodes for our group, then he's going to have a partition created for us on which I'll have exclusive access to. If you don't have access to that, you can't run it, because your user ID will be hard-coded in the scheduler to use that particular partition. So you shouldn't use it, because even if you use the wrong partition, it's just not going to run. You're just going to stay in the queue forever. So those are some of the issues that we ran into. So for further information, you can contact that particular email, and that's it. Any questions?
I've been asking a lot of questions, but I still have time. I'll give you a case study. How about that?
That's fine.
I've been working with Amy for a while, but this topic more specifically recently. And in George's talk, he talked about the 3% versus the 97%.
Mm-hmm.
I consider myself the 97%, where most of my work can be done on my PC. However, there's certain jobs that really can take my computer all day, maybe more. and trying to find that balance of what tools to use, cores to use, GPUs, blah, 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 I think is a kind of a hard conversation for a lot of people who
Yes.
do not have this kind of background. So kind of a two-part question. One, do you have advice for somebody to learn about what they need? And then two, like, there's different types of calculations. You mentioned a few of them. I give my case study is I use hyperspectral imagery. There's like 40 gigs, and it's like billions of pixels. But the calculations are fairly simple. They're not, simulations.
So your bottleneck is mostly data.
It's heavy data, simple computation.
Yeah.
But they can take 8-10 hours on my PC. This is the case study. So there's the general, what I
Right.
asked about, like general resources about, well, what if I do want to run simulation or whatever, but knowing what tools to use without using too many, right? Trying to find that perfect fit.
Right. So for your use case, if your PC has a dedicated graphics card, you can use NVIDIA's CUDA toolkit to use a compute cores if you have on it. Like
And I do
a graphics card like that may cost like
but
$300-500.
And I don't know how to make that bridge, right? So that's kind of the issues for me is I do most of it in R. It's fairly efficient, but how do I tap into the micro?
Here is one of the issues that we have run into is MATLAB, some of the other GUI applications, they are mostly designed to run in serial mode. To run them in batch and parallel, you have to jump through a few hoops, I'm guessing.
I think there are a few packages in R specifically that does parallel on your own computer. It may be something similar like your OpenMP. I have not run that
Well,
yet.
all of these programs, they will use either OpenMP or OpenMP in some format or the other. They don't directly do it. They leverage these libraries to do that.
What form is your data in? Is it like a
TIFF
file?
TIFF.
Okay.
GeoTIFF, I guess technically, because
Oh,
spatial data.
Okay, yeah. So essentially, each pixel you have is an integer, probably 0 to 655, 36, or something, however many digits
Could be
you have.
doubles too, depending on.
I don't know, it's double precision for
Yeah, it could be,
numbers.
yeah.
Okay.
But we can start with integer if that's.
No, I'm actually trying to figure out what type of information you've got. So there's never one answer, and the simplest, quickest way would be to, again, if the ARC cluster was bigger, you can do what's called high throughput computing. So each one of these images, you're doing the same thing. So you create the bash shell script that he talked about, and essentially each time the script runs, it has a different parameter, it has a different file name. So you do the same thing, and then you, however many slots you have in the cluster, maybe you're just running on one node, you got 32 cores, and you got 32 of these running in one time. So that's high throughput computing. The high performance computing is more what he was talking about, where you either have node level parallelization, that's the OpenMP, or you have distributed parallelization, okay? And he described how you cut up your project and you spread it across the pieces, and then you work on the pieces in parallel. A real good analogy of that is to putting together a jigsaw puzzle. So one person working on a jigsaw puzzle can take a long time. That's the serial process. The parallel processing is to take 4 people, cut up the pieces, give them to each person does their part, and then you bring it all together. Okay, so that's the parallelization. And tying back into your question is the linear cores. In that state, it's pretty much linear, but at some point it will turn over, as we call it. So if it's perfectly linear, that scale, we say that's perfectly scaled. So 4 at 4 times 1/4. If you have 20, it's 1/20th, but things don't ever scale that much. At some point, it turns over. Your problem, it might be 4 cores, or maybe it's 1,024 cores. So not all these models can really parallelize out to these large spaces. So another solution is to use the GPUs. Like you mentioned, you could use the GPU in your workstation or your laptop. You have to have that software installed there. You have to code to use those libraries to do that. So it's not a simple thing. It's just, oh, I'm going to throw 1,000 jobs in the queue, and tomorrow I'll come in, they'll all be done, you know. But if you were to actually program the GPU to do that calculation, then in a matter of seconds, they're all done. Okay, or at least it'll take seconds per image to do that. And you'll still have to look through each of your images. Now, the way the GPU works is, these things are graphics cards, is what they are. And if you think about it, each pixel on your monitor is a floating point number, okay? And a GPU card is a floating point calculation. So each pixel is a little floating point calculator. So what you're doing is some kind of mathematical manipulation on each one of these pixels. So if you have 1,000 little pixel operators operating, you're going to run 1,000 times faster. Okay, so learning to program that GPU to do this work is worth your effort, but it's a very high hurdle. And one of the things that I was talking about in the talk this morning is that UC needs to develop this infrastructure so that when you have this question, you're not the only one asking this question, okay? So you need somebody in central computing or somewhere that knows how to do this, okay? I know conceptually how to do it, but I couldn't do it myself. I know who I go ask it on you. He's like 6 desks over, okay? But, so that's, there's a couple ways to tackle this. Did that answer your question?
Yeah. I mean, it definitely answered my specific question. And again, thinking more services for us to answer these questions for others. I mean, it looks like we do need a little bit more development of our own skill sets on how to tackle these questions.
Right.
But one of the things that for me was just the GPU. You answered mine very specifically, right? It sounds like I'm using homogeneous, fairly simple calculations. A GPU is exactly what I need, and I probably my workstation is perfect for that. If I had that
If you have an
initial
NVIDIA card, I don't know if you do.
I think so, but it may be fairly small, maybe a little old. But it still sounds like it could absolutely reduce my
if you use
computational needs.
NVIDIA toolkit, it will just immediately tell you how many computing cores you have in it. So you can parallelize it for that.
But I don't think, I will say this pretty bluntly, most people, most faculty know the solutions. They would have to ask somebody like you and say, here's my specific problem. How do I solve this? What's the best way? And it sounds like it's really cool that maybe I don't need to be on ARC at all, so I can save that resources for others if I can tap into my own GPU. And that's really, really valuable just right there. So for us, we need to spend some time learning that so we can tell others, well, and then of course have somebody that can help us get that GPU.
Jet stream.
The ARC does have GPU, so I think it's got 2.
Yeah, but it's right there.
Right.
Yeah,
See,
but
it's
Research facilitation
Yeah.
piece.
So this is really helpful.
I had a fundamental lesson there. That happened at older. I often find, and I can almost say with 100% surety, that I'm not always the first one to want to do this. So if you go ask the Google machine, you will probably find somebody that hasn't done this. And, but never am I the only one with this problem. So it's just struggling to find whether that resource is at, on this campus or at the larger. And maybe that's another benefit that the centralized computing folks, because they're already tapped into these corners, these mailing lists, and they know who to go ask at NVIDIA. But, R is probably the most common programming language that for researchers. Video card and programming NVIDIA graphics cards is one of the increasing skill sets problems. It's a great tool to apply to lots of different problems. And so somebody's married that already. So, yeah.
That was perfect. I mean, that's to me is the general question is for when somebody asks me about a specific use case or asks Amy about a specific use case, us knowing general rules of thumb on things like, oh, you should use about this many cores, or you should use GPUs, or maybe we should work on your specific machine. Again, thinking more generally now about we don't need to know exacts. That's where we have expertise, like you guys.
So one thing I wanted to add to that is if someone, general rule of thumb, if someone is trying to do data mining, image manipulation, artificial, GPUs do very well in that. But where the CPUs are really important is when you have differential equations with a lot of physics involved. Like those differential equations are sometimes they can be disparate. The scales are too different. The DNA scales I just showed you, just saw the time and length scales, right? They're too disparate. Every time I even stray a bit from here to there, the code is going to fail. I have to make sure I conform to certain restrictions based on that. So the only time I can use that is based on CPUs. I can't go to GPUs with that because it's not going to be able to handle the level of stiffness, as we call it.
I think you guys have answered my question very specifically too, is most of the people that I interact with are not thermodynamics, physics, astronomers. Those people are the ones who need these parallel computings, it sounds like, the CPUs, right? Versus...
So, just for an example, it is vaporizing here, right? So it is going from liquid to vapor. That stiffness right there itself, a GPU will not be able to handle that as efficient as a CPU.
So I think investing in this conversion of people's personal laptops with GPUs is a very easy win for us if we can figure out a way to do that, to help optimize their individual systems they already own. Mm-hmm. Is that like a good sentence to say out loud?
Yeah.
Okay.
You might still need a bit more powerful...
Well, it's getting somebody that knows the CUDA libraries and programming language.
Yeah.
And so just finding examples, installing the software on your laptop is probably pretty easy. Okay, it'll just work. But it's having that code to actually take your data and run it on that graphics card. I'm sure it's up there.
But that's excellent. That's a huge step to get some of that 97%, I think.
So I had a couple of thoughts in that, okay, we have the 3% and the 97%. Okay, and when we looked at the statistics on our research computing systems, we had just maybe 2 handfuls or a score of people that would actually do this parallel programming. And they're using 80% of the core hours on a system. Okay, so that's maybe 20 people. And this is the kind of stuff the engineers and the physicists do. Okay, if you think about calculating the structure of the universe, it's a pretty big problem. Even the weather. Okay, that's where the weather touches everybody's life. Okay, and so that's always the example I give in these type of talks. But, okay, so you have a handful of people using 85% of the resources, they need that. But the other 15% are producing more papers. Okay? They're not using as much resources. They don't need as big a hammer or big a wrench to tackle their problems. So having smaller resources, they can get a lot of work done. So
that's a really good point. And the other thing that I think about too is I do a lot of 2-dimensional, because of aerial imagery, I'm looking at things in 2 dimensions. But there are tools that can do 3 dimensions, but I may not be able to accomplish them given my limited resources. So this is where maybe as somebody who didn't traditionally use them, could use them now going forward because I have the computational power. And maybe that allows us to be more productive in research. But that's a hard bridge to have, going from something that's traditional to teaching them a new skill and then expecting them to use that new skill to create new knowledge that's new to their field.
Right.
That's the goal, right? I hope, but that's
One big bottleneck you'll immediately face when you go from 2D to 3D is memory issues.
Yeah.
So
it's an exponential growing
that's this case you're seeing, I just ran it in 2D.
Yeah.
And the data file is somewhere around 100 MB or less than that. If I make it in 3D, that goes to 3 gigs.
Yeah.
And the bigger problem I have after that is I have to load that 3 gig file, at least 10 or 20 of those, into memory when I'm doing my machine learning type of stuff. So it won't run. If you only have 32 gigs or 60, it's not going to be able to handle that.
So for 3D, are you talking photogrammetry?
Yeah, so we do a lot of LiDAR as well.
Okay.
And so it would be collected in guess 2D, but you could extrapolate into 3 dimensions because of the data that you
Yeah,
collected.
it is.
And that's where, you know, your simulations, that's where your calculations would be, do the extrapolation.
Because we at IU, photogrammetry is a big thing. And that's where they do it from, like, for aerial stuff, you'll take many aerial photographs of like a building, and then you reconstruct 3-dimensionally that
Yeah,
building.
even like
Okay.
drones are really popular.
Yeah, exactly, with drones
2
being
centimeter
popular.
pixels.
Or you could take like pictures all the way around something, and then using photogrammetry recreate
Exactly.
that 3-dimensional.
And this is
and then
where-
you send it off to a 3D print.
And that's where like the limited, where a lot of us are stuck to get there because of computation and their own skill sets.
So another option is that my advisor and I ran across is when we were trying to do this, we needed 1 terabyte of just memory. So we just bought a small,
1 terabyte?
yeah, I have that. So what he did was
Just
like,
get cheaper, but
yeah, he got me a $20,000 system that has got 20 cores and 1 terabyte of RAM so that I can load all of the data into the physical memory. So what I'm saying is, if you are not looking at something like where you need a lot of computing space, a small computer with a lot of RAM might do, it's just a use case, I'm telling you. It might just help you, you know, like, okay, because when I'm doing machine learning on this, I can achieve, like this took me them 30 days to do this on 220 cores, right? And on machine learning on the same thing, I can run it in 30 hours on 16 cores or 20 cores. The same thing, and I can give more results. So you can see the difference, right? So if I'm only using 16 or 20 cores or something like, I don't want to use the cluster. Why should I waste someone else's time, right? Kind of thing. So it depends on how you want to do it again.
I'm still processing, sorry. There's a lot for me to think about.
So,
too, from both my personal use, but also as the service provider as well. It's
So-
hard to balance those worlds sometimes.
So one of the things we did was like, you know, when we asked them was, we wanted them to do a scaling study it's a different type of thing. What we asked them was like 1 terabyte, 2 terabyte, 3 terabyte, how much is it going to cost? 1 terabyte was 20, 2 terabyte was somewhere around 48 or something, and 3 terabyte was, it was like 100 grand or something. So we stuck to the 1 terabyte. We just wanted to make sure we get an idea of where we are going.
But that's also why I think, you know, her unit is trying to have these centralized resources so people like me who want to try something new don't have to invest $20,000 to try it. That may not even be successful, right?
Yeah.
Yeah, so that's kind of, I think, this is more the service provider, but, you know.
Right, that was
provider
before the
can
ARC was even
almost-
there.
Sorry?
He got me that computer, or we had that computer before ARC even existed.
Yeah.
So we wanted to run on something to make sure that we were able to get the
So I think the goal is someday that the ARC, well, whatever it becomes named, that resource will be big enough that it's not this competition resource right now. So, you know, everybody's sort of
That's tough.
fighting for the same 3 peanuts.
I think you mentioned that too, with audits for departments. I mean, I know certain departments have their own mini HPC setups or a bunch of cores or something. And yeah, that's more her world. So,
Yeah, well,
but we're so connected, so it's very, very interesting.
One other thing we did was like, you know, we had
Yeah.
a lot of old hardware lying around, like, you know, old desktop systems or something. So someone had the idea of like, you know, stitching them together using LAN, or like you have those 24 switch routers, right? So they tried to see if they could get a small cluster up and running with that. Those are 10-year-old systems, so I don't know.
It's just the barriers. I mean, the barriers are going from somebody who doesn't program at all to maybe learn to program something like Python or R, MATLAB, etc. But then thinking even beyond that. And they're just barriers for people who have expertise in things that may not have the technical skills to go along with them. And I think that's what we're trying to do. Both of our groups are trying to support both sides of that. And it's tough. It's tough to do. But there's so much potential there, and it really, this is inspiring. So I'm glad you guys
Good.
came. Yeah, this is really great.
Success.
So yeah, so if you really want to learn Linux, I'd say go for this.
So I did try. I had a really old computer that literally was so slow that it couldn't run Windows. So I installed Linux, runs just fine, but I can't figure out how to use it very well.
So this device also has Wi-Fi on it. So you just, once you set it up, right, just connect it to the power and put it in the corner, and you can forget, you can just remote log into the terminal for that. So you don't even have to worry about it.
Can't do everything.
I found this really useful
Unfortunately.
to like
Yeah, I got a
teach.
day job. Getting in the way of things I want to do.
But
One other thing you can also do is you can install virtual machines on your own laptop to just learn. I mean, it's just going to use share the resources with your existing operating system, what you already have, but it's another way of speeding up your learning process.
well, and this is one of the things I tried was I did a mini version with Jetstream. That's one of the things we worked on together, and I used the one I didn't have to request.
Yeah.
The very basic one. But what did I say? It took 10 minutes there, but it took 11 seconds on my computer for the
Yeah.
very free version. So this is.
I'll share this with you.
I annotated my process.
Documented it, yeah.
So this was another reason why I wanted to make sure that I made it here. Sorry I didn't make it yesterday because it's cat killer. But trying to think about that process and finding that perfect balance. But it sounds like there's a really interesting opportunity here for me. For me personally, it was the GPU thing. So that's really exciting for me that I can not have to tap into other resources since I have a decent machine already. But there's going to be people who have different problems that I want to be able to say like, oh, using this level at Jetstream is exactly what you need. And then they have support, So kind of finding the balance,
Yeah, that little allocation is there, nothing more than to wet your appetite.
But I was able to go through the whole process fairly quickly. I don't remember how long it took me to go through, but including uploading my own data, which was, again, I'm very data heavy, not necessarily computation heavy. So that's also interesting to think there's going to be two different worlds. There's going to be people who are running, scripts that run, there is no data, it's just scripts and
So
calculations.
that DNS file I just showed, case I just showed you, this one, all the script files together are less than 500 KB.
Yeah.
But when I run it, it gives me somewhere around 100 gigs of data.
Yeah, exactly. And I'm kind of the opposite.
Yeah.
It's really interesting. So, and we're
Well,
on campus.
what's going to be important for you is when we get some centralized storage so that you have a place to store that large amount of data too. Right now, probably on your workstation, bunch
Yeah, I have
of
a-
gig disks or,
external hard drive. It's like a
Yeah.
terabyte, but then it takes time to get that from my external hard drive to my computer, and that's
and that's the beauty of having centralized architecture in that you have the archive storage, which you can put stuff there. It can take days, maybe minutes, hours, days to pull data off. But then it's on this high-speed parallel file system that you can work on it very quickly, and get your answers, and it's all tied together with high-speed networks.
yeah, that's another limitation for us too. I mean, I don't know
Yeah.
what we have back there, 100 megs, maybe
Sure. No, go ahead.
megabytes. I mean, I'm just regular. I'm
Yeah.
not on
I
any
think
node or anything.
I think if you got the upgrade, you have 1 gig.
Yeah.
It's
Small
like,
syntax problem.
Some of my limitations is
Yeah, that's
down.
where you get married to discussion. That's like lighting a fire on a short fuse.
Well, it's funny is I do some work with the Army Corps.
Okay.
And this is where the imagery comes in. So they have hyperspectral, an imager, it's a drone that has 200 and something bands.
Uh-huh.
And the pixel sizes are 2.3 centimeters apiece. It's
Okay.
like a football field, and it's 40 gigs. It's crazy. It's such a small image, but it's so dense. But being able to run these kind of algorithms and processes on them allow us to test things that we've never tested before. So, we have kind of, I think it's like very cyclical, like where the tools allow you to try new things, and then you kind of plateau there, and then your research needs to expand to new ideas, and then your tools expand, and kind of this
one other general rule of thumb is in HPC, if you're doing more CPU related tasks work really well with C and Fortran. It's a general rule of thumb. But if you're doing more image processing type of things and want to use PyCode, Python works better.
Yeah.
So and Python can still be used. This is what I use Python to do machine learning on
And
it,
a lot
but
of
use
packages for
CPUs.
R and Python are built on C and Fortran anyways, right?
And the advantage of Python is let us say your computer has 20 cores, right? And if you use some of the library mode, it automatically divides it. You don't have to explicitly use OpenMP or OpenMPI. Python uses them through NumPy or some of their other libraries.
Well,
So
it's good having some use cases, so.
Well, and that's exactly what I'm working with her and her group, which I guess then is working with you and your team there, is developing these use cases and trying to tap into people that, again, are different than this. Because I think this is what people have been using for, a decade now, maybe more. These are the types, the astronomers, the dynamics, engineers. I think this is more common. But there's a lot of us out there that are like, oh, that sounds cool, but that's not for me.
Right.
But then you're like sitting on your computer for 12 hours and you're like not doing anything. So trying to find that balance. And that's, and again, I'm in the libraries, so I'm also a service provider. So I'm not just thinking as a researcher, I'm thinking of how to help other researchers who have needs that I don't even know yet.
And
We still just started this a couple of years, like a year or so back, right? So we're still running into a lot of issues we have not seen before. So we're still trying to address that. So, questions?
Are we concluded? Questions?
I'm going to ask him a question later
Okay.
after you're done.
Oh, I'm just chatting now, sorry.
I think-
Yeah, we're
That's
just
fine.
Thank you, Himakar.
Thank
Sure.
you.
Thank you.